Okay, hello everyone. It's my great pleasure to give a talk in this tutorial. I'm Lei Wang from University of Wollongong, Australia. So just now, Peter has given a very insightful introduction on power normalization. So now I would like to briefly talk about the development of SPD matrix-based feature representation, and also talk about our work on kernel matrix-based feature representation for fine-grained image recognition. Okay, from previous talks, we have well understood that the fine-grained image recognition is quite different from generic image recognition because it has larger intra-class variation, but smaller inter-class variation. So it has many real applications. It's quite important. We know that, okay, similar to generic image recognition, the feature is very important, but because the characteristics of fine-grained image recognition, feature becomes even more important with feature, and a feature. But generally, in computer vision, okay, extracting good features has been a central issue during the development of this field. Feature extraction is very important because we know that it's not easy to describe an image due to all kinds of variation, rotation, illumination, among others. Generally speaking, during the development of computer vision, we can categorize the feature representation into three stages. So the first one is before year 2000. At that time, people use handcrafted global features, for example, histograms, texture features, or shape features. But from the beginning, we know that we need to extract invariant and discriminative features. So this is our goal. And then between year 2000 and the year 2010, it is a heyday of backwards model or backward features model. People use local invariant features because they are more robust against the change of view, change of rotation, or scale, illumination, or cluster. So we have seen the popularity of backwards model in that decade. Since year 2012, the computer vision community has embraced deep learning. So we see that we use deep learning, deep neural networks to learn better feature representations for images. So generally, we obtained the 3D convolutional feature maps. We look into that 3D convolutional feature map. We know it has width, it has height, and it has depth. So again, we can interpret it as a set of deep local descriptors. The dimension of each descriptor is the depth. The total number of descriptors is width by height. So we represent an image into a set of local descriptors, very similar to the SIFT features during the heyday of backwards model. Then a question we cannot avoid is how to pull a set of local descriptors into a global vision, because we want to affect this set of local descriptors into full connect layers, then softmax layers, then make a prediction. Then we see that we use max pooling, we use average pooling, or something in between, for example, GM pooling. We regard this kind of pooling method as first order method because they focus on the information from each individual channels. Okay, but in order to extract the better features or more sophisticated features, especially for the applications of fine-grained image recognition, we need to consider the correlation among different channels. So this gives rise to covariance pooling. We call it second-order pooling because it considers the correlation among different channels. So this brings the covariance matrix-based feature representation. Right? Actually, covariance matrix-based feature representation was proposed much earlier than deep learning. So at the beginning, the covariance matrix was just estimated from the pixel values or from the gradient of intensity values. So when we have an image, right? Okay, so conceptually, covariance matrix is quite easy to compute. So this is a definition of covariance matrix. So we can use statistics and the knowledge of Gaussian distribution to obtain the covariance matrix images. On the diagonal, it is a variance. On the opposite diagonal, it's a variance between different feature components. But a very important point for covariance matrix is not every matrix can be a covariance matrix, because covariance matrix is SPD, symmetric to positive definite. So that means it is not full of the whole matrix space. Instead, it resides on a subdimensional manifold. So then, at the beginning of the research of covariance matrix-based image representation, how to measure the similarity of two SPD matrices, to decide the similarity of two images, one of the key topics. So in the literature, we have seen the geodesic distance method or Euclidean mapping method or kernel method. I just give a very brief introduction. The geodesic distance method was proposed during 2003 to 2006. It's mainly studied by researchers from the area of medical image analysis. Then after that, from 2005 and to 2008, the Euclidean mapping method was proposed and very popular. The basic idea is to map the covariance matrix from its manifold to its tangent, then to much easier. And we know the log Euclidean matrix is a typical method of this point. Then after that, from 2011 to 2014 or later, kernel-based methods become the basic idea is, since it is not easy to evaluate the similarity between two covariants along its manifold, so let's use the trick of kernel from support vector machine to map each covariance matrix onto a high dimensional space. Then we can use inner product, or you can measure their similarity in that space. It's quite convenient and it can have theoretical guarantee, and it's almost quite good performance. Then from year 2015, we see the integration between covariance matrix-based image representation and deep learning. So since then, this has been well studied. From the beginning, researchers focused on the structure of the deep neural networks to accommodate the covariance matrix. And also, how do we do the matrix backpropagation to ensure end-to-end learning? Then we move to the topics such as how can we do this kind of backpropagation very efficiently? How can we handle large covariance? You can see that there's still a very active research topic in major computer vision conferences and major computer vision journals. Now I would like to talk about a piece of work we have done on covariance matrix. Actually, we replace covariance matrix with kernel matrix. Okay. So if we look into covariance representation, we can find that actually, if we look the I and the J entry, the covariance matrix, we can write this entry in a linear function. It's just an inner product. Inner product between the two realization of I's feature and the J feature. So once we have this expression, we understand that the covariance matrix just model the linear correlation of I and the J feature. But the problem is we cannot ensure in real applications the correlation between the ith and the jth features. For example, the ith channel and the jth channel, their correlation is just linear. What if there is nonlinear correlation? And also another drawback of the covariance representation is this kind of expression is fixed. So regardless the domain knowledge, regardless of that thing. And also because the rank deficiency issue, when the number of samples is not large enough, usually the covariance estimate will end up with unreliable or even being single. So then we propose, okay, since this is a linear product, only model linear correlation, then we can use a kernel tree to just replace this inner product, okay, into a kernel, okay, kernel ID. So that means we replace this inner product with a kernel function. So actually we move beyond covariance matrix to a kernel matrix, and any kernel matrix is an SPD matrix, and any SPD matrix can be interpreted as a matrix. So actually we expanded the domain from covariance matrix-based feature representation into SPD matrix feature representation. So the advantage is we can freely model the nonlinear relationship between features. And also for many kernels, we can prove that theoretically that the matrix M obtained guaranteed to be non-single, regardless, okay, what the feature dimension is and what the sample size is. So this is very good. Also, we does not change the size of the covariance matrix. It's still D by D, right? D is the dimension of the descriptor. So we maintain the computational cost, okay, of the covariance matrix. So we proposed this idea in ICCV 2015. During that time, the deep learning-based method just started, but was not very popular. So we just test this idea on traditional features. For example, for skeletal action recognition, we use the joint features to represent the action. But we can see clearly the advantage of using the kernel matrix to replace covariance. For example, compared with the covariance-based representation, if we use kernel representation, we can see more than 20%, 20 percentage point absolute improvement. For other data sets, we still can see more than 10%. Also, we tested on more skeletal action recognition data set, we obtained significant improvement. So actually, we believe that this method is among the leading ones, okay, before the era of deep learning. It does not need any data to learn. It's still handcrafted. It does not need to use many data. So you can directly extract features and still obtain quite a good performance. So if that means it will be useful for complex systems that cannot access enough skeletal data to train a large neural. We also apply this kernel matrix-based feature representation to generic image, for example, texture, face, object, they still can obtain. Then when we have deep neural network, for example, pre-trained AlexNet or VGGNet, we use them as a feature extractor to extract features. Then we apply covariance matrix or apply feature vector or apply our kernel matrix-based them and compare them, then we still find that okay, the kernel-based feature representation still gives the best performance on pre-extracted deep feature method. Now I would like to move to deep learning era. Since 2015, we can see the integration between deep learning and second-order pooling. This is a milestone work in this regard, and also it is proposed for fine-grained visual recognition. So following that, actually, in the same year, ICCV 2015, this is another milestone work. It investigates an important issue. How can we conduct end-to-end learning? So how can we derive the matrix-based backpropagation? Because in this case, we have to process matrix, because covariance matrix is a matrix. We have to do matrix normalization as discussed in Peter's talk, logarithms or eigen decomposition, how we can propagate the gradient from the arrow function, okay, to the convolutional layers of the early. Then after that, in 2017 or 2018, we see the more and more methods, okay, proposed. Now I would like to introduce one of the pieces of our work, okay, we proposed in ECCV 2020. So we have seen the promising performance of kernel matrix-based SPD replication, but not learned in an end-to-end manner. It's still applied to either handcrafted features or the pre-extracted learning features. So we want to put it into the deep learning neural network and learn it in end-to-end manner. So this is our motivation for this work. And also we have been aware that the existing matrix backpropagation, okay, could cause some numerical stability issue. We have seen some complaint in the recent literature. So we would like to look into this issue, okay, in our study. So that's two are the motivation of this piece. So again, you can see that our deep neural network follows the mainstream structure. That is, image go through a backbone, for example, VGG16, then we obtain the last convolutional feature maps. Then we reshape this convolutional feature maps into a set of three-dimensional deep local descriptors. Then based on them, we can calculate the covariance matrix or calculate the kernel matrix. Here, we calculate the Gaussian RBF-based kernel matrix. So we have L2 normalization layer to ensure that we can normalize all the local descriptors into the working range of Gaussian RBF. Then we calculate Gaussian RBF kernel, then we have to do matrix normalization, for example, matrix logarithm or matrix rooting to adjust it. Then we take the up triangle, then reshape it into a long vector, then batch normalization, then we into full connect layers to softmax layers to make prediction. The whole structure is okay, the mainstream structure. So what we have to do is to derive the matrix backpropagation. For example, this is the data X, is a convolutional feature. So we go through the X to another step. This is just a data flow. Okay, another step, then calculate the Euclidean distance matrix, apply the exponential. This makes it a Gaussian RBF. Then we fit in matrix normalization, reshape, then full connect layer softmax the loss function. So we have to derive the gradients of the loss function with respect, right? So convolution layer. That means we have to go through the intermediate step. So we derive them, okay, step by step in our paper. So in particular, the one of our contribution and also the one of the key obstacle is how do we pass, backpropagate the arrow signal or the gradient through this layer. So this layer actually is a matrix normalization layer. Okay. So matrix normalization involves eigen decomposition and then apply a function, for example, logarithm function on the diagonal, the eigenvalues. So how can we bypass? How can we backpropagate the arrow through this step? So in the literature, as I mentioned, the ICCV 25 is a milestone work. it has given a very detailed derivation about this matrix backpropagation. Very useful. But actually, it has some problem is it defines a key quantity in this way. There's eigenvalues, I and j, that inverse. So in this case, if the eigenvalues are similar to each other, you could end with infinite value. So this causes numerical instability. So by studying the literature of positive definite matrix, actually we find that this kind of gradient issue has been studied in the literature in 1950s by researchers, okay, on operator theory, okay, mathematicians on operator theory. So they derived that the relationship between these two layers. Although at that time we don't have deep neural networks, we don't have covariance pooling, but we have this kind of relationship. And in their relationship, they define this key quantity. In this way, actually, we find that by using L'Hopital rule, it can avoid the numerical instability. So since now we have two results for the same problem, one is from ICCV 2015, the other one is from 1950. So we are interested in what the relationship between these two results. In our work, we derive the relationship between this. We find that both of them are right. So actually, the only difference is the milestone work in ICCV 2015, they actually did not merge some terms to approach, okay, the expression given by the 1950s result. But we close this, show the identity. Okay, now I would like to show the result. We apply the kernel idea into the deep learning, and we learn them in an end-to-end manner. So this is the result, but I would like to highlight this result is in year 2018, which is not the state of art. Understand, we can obtain better performance now. But from this table, we can see that by putting the kernel matrix-based feature representation into deep neural networks and learn it in end-to-end manner, we can obtain our performance in aging. Clearly see its performance on those fine-grained image recognition data set. So it's improvement with respect to the relevant method. Also, we compare the stability obtained from the two different results. We can clearly see that with the number of epochs, the classification error on validation data set, we can see that by using our method, okay, obtained from 1950s, okay, we can obtain lower, consistently lower classification error to the number of epochs. And also we compare the deep KSPD versus deep COV to show that whether we really need the kernel matrix-based feature representation in deep learning neural networks versus the covariance matrix. Again, we can see that even if we put both covariance matrix or kernel matrix into deep learning and then learn them into an end-to-end manner, we can still obtain performance by kernel-based. That means extracting the nonlinear relationship between different feature channels is still important in deep neural networks. Okay, just some take-home messages. So we can see that the second-order pooling, covariance pooling, or kernel matrix-based pooling become a very interesting and important topic for fine-grained image recognition or generic image recognition. So we have seen that how to efficiently train the SPD structure layers become important. How can we further consider higher order correlation is also another topic. And actually there have been many papers discussing this issue in recent literature. Also, we are interested in the relationship between this kind of method with other important, for example, attention, non-local graph neural networks, and bi-level optimization. Also, as we have seen from Peter's talk, the second order pooling and higher order pooling have been applied to applications outside of fine-grained image recognition, image segmentation, person re-ID or retrieval of few shots. We believe that more and more computer vision tasks will take the advantage of second order pooling and higher order. Okay. So this is a list of the publications related to what I have discussed in this talk. Again, I would like to draw your attention to this website. We collect the SPD papers and the works. Okay, in this website, we compare them and list them. So if you are interested, you are welcome to visit our SPD representation method. Thank you, everyone. This is my talk.